Welcome everyone. Welcome to this last and 10th video in this 10-part series on convective wildfires. My name is Castellnou, and today we are going to look into real observations of pyro-convection using the knowledge on conserved variables that we discussed in the last video. Before we dive into the measurements themselves, I would like to highlight this paper by Mark Castellnou, which is a recent one, still a preprint, but it's a very nice paper in which he discusses sounding measurements from Europe and Chile over the past 5 fire seasons. So it includes a lot of data. The nice thing about this paper is that it first of all starts with a conceptual figure in which he shows what you can see from a single sounding measurement. And I think that this part is relatively easy for most of you after watching this series, as we have discussed most of this in this video series so far. But what is maybe even more interesting to most of you is the connection to actual case studies. So there are several case studies discussed in this paper where the sounding measurements are connected to the actual observed convective plumes and to the subsequent operational decisions that were made. So if you want to have a deeper dive, take a look at this paper. In this video, we will focus on the basic information that one can get from these soundings due to the time limitations. But if you want to know all the details and everything you can learn from them, have a look at this paper. To start with interpreting measurements from soundings, I want to start with an environmental profile. And when we start to look at soundings, we typically first of all look at the potential temperature profile, as it tells us something about the vertical structure of the atmosphere. And if we look here at this potential temperature profile, we can at the bottom first of all see a surface layer in the lower 150 to 100 meters, right? Then we see a somewhat mixed layer, which indicates the presence of a convective boundary layer here, which afterwards we see somewhat of an inversion. But the thing is, where do we exactly put this ABL, right? Because you could also argue maybe the convective boundary layer had the top is here already instead of a few meters above. So in these kind of cases where it's not extremely clear where the convective boundary layer is based on the potential temperature profile, the other thing we can look at, if you remember the previous videos, is the specific humidity. Because we know from moisture that for the atmosphere, the only source of moisture is the Earth's surface. So closest in the boundary layer, we find the highest amount of specific humidity. In this case, if we look at this profile, we see near the surface an enormous peak in specific humidity. We see kind of a mixed layer where the specific humidity is relatively constant over height, and then just below 400 meters altitude, we see an extreme drop in specific humidity, indicating the top of the convective boundary layer at this specific height, supporting our finding of the convective boundary layer height based on the potential temperature profile. So here you see that sometimes the potential temperature profile can be sufficient, but the sounding also always measures the specific humidity. And this can really help in understanding the vertical profile of the environment. So the open question now is, of course, can we also see clouds in our measurements, right? And to do this, we cannot look at the specific humidity itself, because in itself, it does not really tell you whether we are at 100% saturation or not. And nicely enough, the soundings also always provide a relative humidity output. So when looking into that, we can determine whether or not we have clouds. Here, this relative humidity profile is from the same sounding measurements of the specific humidity and potential temperature that I showed before. And what we see here is a relative humidity peaking at around 90%. And so here at this moment, we did not have clouds anymore, but a few hours back, we also measured the vertical profile of the atmosphere. This is approximately 3 hours earlier, and here we see a completely different relative humidity profile, which is far more moist, right? So we see that between around 300 meters and let's say 500 meters, we have a 200-meter thick cloud layer, which we can see from relative humidity that reaches almost 100%. And please note that theoretically, of course, I mentioned before that clouds form when the relative humidity becomes 100%, but with sensors, they're not 100% accurate, right? So this close to 100% indicates clouds. And the nice thing here, and this is something I would like to emphasize, is if you want to test this out and you want to see and get a feeling for the equipment, take a day where you have clouds and no clouds, and launch a sounding during the period that there are clouds, and launch a sounding when the clouds are gone, and see what is the difference. What did I actually measure? To get a feeling for what you measure when you actually release it into a plume with or without clouds, right? And the nice thing here is that you don't have the dangerous conditions that come with fires, but you can still test the theory that we described in this series. Now the question is, if we actually move from environmental soundings to soundings that we release into a convective plume, what would be the difference? The main impact of pyro-convection on the sounding is the increase in rising speed of the sounding, because the core of the convective plume rises much faster than the normal environment, right? So when we release a sounding into the environment, it will typically rise with a 1.5 to 2.5 meter per second rising speed. However, when we release the same sounding into a convective plume, we will see that inside the convective plume, the rising speed will be higher than 2 meters per second, as here indicated with the red dots. And the nice thing about this is that it also provides an estimate of the plume top of the convective plume, right? Because that is the point where the rising speed will go back to normal, to around 1.5 to 2.5 meters per second. So in this case, we could estimate the plume top to be around 1400 meters. So the next step is to understand the potential temperature profile that the sounding measured while it went into the plume. And interestingly enough, when we look at the surface, we see an increase in temperature in the first 2 to 300 meters, right? And this coincides very nicely with the acceleration in rising speed in the lower 2 to 300 meters. And this acceleration in rising speed indicates that it went from the environment into this convective core of the plume, meaning that the rising of the sounding accelerated while it went into the plume, which is very logical. And this also explains this increase in potential temperature of a few degrees, because it went from ambient temperatures to in-plume temperatures, which differs a few degrees. And here we just determined, right, that the plume top was around 1400 meters. And we can see that up to around 1400 meters, we have a relatively well-mixed profile, where the temperature is relatively constant with height. And then above it, we see something strange. We see a slight decrease in temperature, and this somehow also is related to vertical velocities of rising speeds around 0 meters per second, even a bit of negative rising speed. So what happens here? And now we have to think back of our atmospheric knowledge, right? We know that above the 1600 meters, we get this inversion. It means, for the sounding, that the sounding is not able to rise further at first. So it will continue to bump up and down around this inversion for a while before it's able to break through. Because of course the helium balloon itself is a buoyant parcel, but it's also affected by the air that goes into here, overshoots the inversion and then goes back, meaning that the sounding will hop up and down around this inversion before it's able to rise any further. And that's exactly what we see here. We see very strange behavior of the rising speed going below zero and then again above zero and then again towards zero, meaning that it's not able to rise any further and just goes up and down around the same level. And that is what an inversion does, right? It inhibits vertical rise, till the point that at a certain point the sounding breaks through the inversion and is able to rise further and measure the vertical profile above the inversion inside the free troposphere. This brings us to the end of the series, where we started with the ancient Greek Archimedes, who came up with the concept of buoyancy, that we were able to use, combined with a football and some water, to explain the observed shape of convective plumes, such as the one during the Pont Vilomara fire in 2022. We looked into how we could predict the ability of fires to create plumes and clouds on top of the plumes using weather predictions that we could get, among others, from sites like windy.com, which provide us with vertical profiles, QTs, from different weather providers such as GFS and ECWMF. From this onward, we went into the current state of science, where we discussed the different types of plumes and their impact on the fire behavior. Lastly, we of course discussed how we could measure them with soundings and how we could interpret the soundings. I hope with this video series, me and Brian were able to give you a coherent understanding of convective wildfire plumes. Of course, this video series is too short to discuss everything. I hope we also provided enough background materials such as the papers that were mentioned during this series. And of course, always feel free to reach out to us personally or to the project. Thank you again for watching, and I hope you enjoyed this video series.